Hello, I'm Renzo Guido. I'm a physics student from Facultad de Ciencias, UDELAR, de Uruguay. I've been working with the nonlinear dynamics group with the people appearing on screen. You may know some of them. I'm presenting a poster in this congress. Let me show you. We studied the development and decay of vortex flows in viscoelastic fluid between concentric cylinders. This is what the poster looks like. The work was mainly experimental, but we also performed simulations. And let me start with the setup. The experimental setup is simple. We had two concentric cylinders, external and motionless one, and an inner cylinder connected to a DC motor. Viscoelastic fluid was filled between the cylinders, and we measured the velocity field, in particular the azimuthal velocity, with the help of a camera, a 45-degree mirror and a green laser, as you can see on the screen. The working fluids were 4 shear thinning solutions of polyacrylamide in mixtures of water and glycerin. I will be referring to the fluids by the amount of polyacrylamide and glycerin content. P1G30 means 1% polyacrylamide added to a solution with 30% glycerin. Now let me show you some of the videos that we recorded in the lab. This one is from the P1G30 solution. As you can see, the inner cylinder abruptly starts rotating, and as time passes we reach a stationary state. Then the cylinder stops and we go back to quiescent fluid. We use digital particle image velocimetry to track particles and obtain the velocity field. As expected, the system had axial symmetry. The video on screen is showing the temporal evolution of the azimuthal velocity for the fluid P1G60, the less elastic fluid. We are showing two different axial distances. All fluids studied present this behavior. Velocity grows until reaching a maximum, then decreases to the steady value. The videos below correspond to the solutions with 2% polyacrylamide added. As you can see, the effect here is quite drastic. The difference between the stationary velocity and the maximum velocity is huge. Now for the decay of the vortex, I will show you the P1G60 fluid and then we will watch the rest of them. The velocity value drops immediately after the cylinder stops rotating, and this strange reverse in the fluid rotations takes place. Again, the other fluids have a more notorious effect. For the higher polyacrylamide fluids, the velocity reverses to a value even higher in magnitude than the previous stationary value. To compare the fluid cinematics, we were inspired by control theory. The difference between the peak and a stationary value, as in the figure, divided by the stationary value, is what we call the overshoot or maximum peak. This non-dimensional parameter depends on axial distance for every fluid. It increases with polyacrylamide content and decreases with solvent viscosity. The simulations we performed with the Aldroyd B model predicted that the overshoot increases with larger elastic numbers. In the figure, you can see that the overshoot is larger for the P2G30 solution, despite it has a smaller elastic number. Then, for a single sample, we studied the overshoot dependence on the rotational velocity of the inner cylinder. Remember that the elastic number is the comparison between the Reynolds and the Deborah number. Both numbers depend on velocity, but the elastic number does not depend on velocity. So again, this effect is not predicted by the Aldroyd B model. And now, moving on to the decay, we define the same parameter but with the minimum velocity, and we will be referring it as undershoot. As you can see, its behavior is very similar to the overshoot case. It increases with polyacrylamide content and decreases with solvent viscosity, but it seems to reach a plateau closer to the inner cylinder. To sum up the results from this study, we first have to notice that viscoelastic flows behave way different than Newtonian flows. This kind of flow have a positive or negative maximum before reaching the stationary value. We show that undershoot and overshoot parameters depend on axial distances, solvent viscosity, and elastic component. Comparing with the simulations we present in the paper, which I invite you to read, we show that Aldroyd B model is not able to capture the full motion of the viscoelastic fluid. Instead, White Maser model, that does contain shear thinning effects, has a much better agreement with experimental data.